plus the nullity is less than or equal. So now the constant is 9e squared, the dimension of the group, and then times -1 plus 1 over 8 pi squared e angles energy. So the constants are a little less verbose. Okay, so what? Yeah, so I understand your question. Where did E come from? Why did that come in? What's going on here is you're estimating the number of negative eigenvalues, and what both proofs use at their core is looking at the trace of some the trace of the heat kernel for some operator. So you look at you're looking at the trace of the heat kernel, and this is why you end up seeing an exponential function. That's exactly where it comes from. Okay, and so in fact, that's also why the Ricci curvature, positive Ricci curvature assumption is necessary in Hirakawa's method. So he also has to do some heat kernel comparison theorem, and that comparison theorem holds for positive Ricci curvature. So again, more or less for reasons of spectral theory, you need to make that curvature assumption. So we bypass that and are able to get by with, again, just positivity of scalar curvature. Let's see where I am. Okay, so maybe what I'll do is, yeah, okay, just trying to figure out how far to go. Let me just tell you the two ingredients. So for the first theorem, so really the proof boils down to this well-known Wagner formula, and then carefully exploiting conformal invariance. That is also used in the proof of this result. So again, choice of conformal representative plays a role. And this choice is in some sense based on the choice in the proof of theorem A, but you need something more. Okay, so I mentioned there's something about estimating the trace of the heat kernel. So what we need is I'll abbreviate it, the CLR estimate, and I'm going to spend some time talking about that in a second half. So this has to do with estimating the number of non-positive eigenvalues of a Schrodinger operator. So in fact, this is mostly what I want to talk about in the second half. So for the last few minutes, because it doesn't take too long to explain this, let me, and it appears in both results, let me talk about this choice of conformal representative. Because the idea is very simple. Okay, so this is an idea that at times, it's the idea to take the Amati problem, and modify it. So let me explain. So suppose I have two metrics that are conformal to one another, and then because I'm going to talk about the scalar curvature, there's a good way of writing the conformal relationship between them to make the formulas turn out nicely. So everything I'm going to do here is eventually going to be dimension 4 for the time being. What I'm going to say now just depends on dimension being at least 3. So suppose I have a metric and I can formally change it, write my conformal factor this way to a new metric g tilde. Then there's this well-known formula that the scalar curvature of this metric is related to the scalar curvature of this metric via some elliptic operator acting on u, and the form that operator takes is some negative power of u here shows up, and then you have a differential operator. Well, I'll write it as call it LGU. So LGU is called the Amati operator or the conformal Laplacian. So it's the Laplace operator. Formula. Right, so times the Laplace operator, and there's a term involving the scalar curvature of the initial metric here, g. Okay, so let lambda 1, well, give me the first eigenvalue. Now this operator has a nice property that is conformally invariant. So if I conformally change the metric, then so the invariance property here, it goes like this, that, what is it I do? Phi to the 4 over n minus 2, g applied to u is phi to the minus n plus 2 over n minus 2 lg du. All right? So it's invariant in this sense. So with these weights. So, but it follows, you can just check that the sign of the first eigenvalue is conformally invariant. All right, then it's the same sign as the Amati constant. Okay, so now what I want to do is I just want to take the scalar curvature that has this nice transformation law and an associated nice operator and add some zero-order terms to it. So instead of just looking at the scalar curvature, I want to look at things that scale the same way but have simpler conformal transformation laws. So, for example, the norm of the Weyl tensor, let's write it this way. So if I can formally change the metric just like I described before, and I look at the corresponding the norm of the Weyl tensor of g tilde, then you'll just have a factor of, what is it, minus 4 over n minus 2 times the norm of the Weyl tensor with respect to g. And then suppose I measure the norm of this, how do we write this, the curvature 2 form. Oops. Then I'll get this. All right, so these transform in a very simple way. So what I can do is just modify, this is the origin of this term, modified Amati problem. I can just look at sort of modified scalar curvature, which is just the scalar curvature, and then minus any multiply like of the norm of the Weyl tensor and norm of the curvature of any given connection you like. And then if I check how this changes under conformal transformation, so g tilde is u to the 4 over n minus 2, then just combining all the formulas I've written down, what you can get is that this transforms in the same exact way as the scalar curvature. You just have to modify the operator appropriately. So you compare with the formula over there, how the scalar curvature changes. I put the same power here, and I'll put an operator. Let me do a script L. And what is script L? So script L is the principal part is the same. So it's minus 4 and minus 1 and minus 2 Laplace plus scalar curvature, and then minus this term here. So you can add these weights that scale in a simple way on a conformal transformation, and it behaves as if you're just looking at the scalar curvature. Okay, so, and because of that conformal transformation law, the same fact holds. So the sign of the first eigenvalue of this operator is conformally invariant. The sign of the script L is also conformally invariant. So, no, excuse me, lambda 1 of script L is conformally invariant. So you get this easy fact. So if given any conformal class of metrics on a compact manifold with dimensions at least 3, then there always exists a conformal metric. So given any conformal class, you can pick out a metric in that conformal class such that this curvature, this modified scalar curvature I just defined there, has fixed signs. So it's either strictly positive on the manifold, identically 0 on the manifold, or negative on that manifold. All right, and in which case it just depends upon the sign of lambda 1. And this is what we're going to use in the proof of both of them, is that we're going to take, you'll see a scalar curvature term in some formula, the Bachner formula or index form, you'll see a scalar curvature term. We're going to modify that scalar curvature by throwing in terms that scale in a simple way. We'll collectively look at this modified scalar curvature. We'll use the fact that any conformal class, we can fix the sign of those terms, this, and this, and then we have to sort of analyze which case we're in. One minor point, it's a bit of a headache. So look, I've taken the norm of things. So in general, that's going to be Lipschitz. So by elliptic regularity, when you prove this might just be a C2 alpha metric. All right. Okay, but then you can just sort of smooth things out, and this case is okay, but here you have to be a little bit careful, right? But then so what you have to do is you have to regularize throughout and take limits. It all works out, but it's a headache that I won't bother mentioning again. Okay, well let me stop here, and I'll pick up with the Bachner formula after the break. All right, so I erased that limit, so I rewrote it over here, so we'll need this eventually, so I'll try to avoid using that board. Okay, so I mentioned for the first result that it's really just an application of this idea about modifying the scalar curvature and then looking at a certain Bachner formula. So let me tell you what that Bachner formula is. So again, this applies for Engel's connection. And it says the following. So I don't have to keep referring to the connection. So let me just write F plus instead of F and plus, too many subscripts and superscripts. So it says the following. I have Laplacian of the norm squared of the self-dual part of the curvature is equal to the covariant norm squared of the covariant derivative. And then now, I mentioned this, there's a term involving the curvature of the bundle. And it shows up as a bracket. So now the bracket gets extended to 2 forms. Right? So this bracket operations on 2 forms. It results in a 2 form, which you then take the inner product of this 2 form. And then, then there's terms which depend upon the curvature of the base manifold. So let me, I'll write kind of again, to make this explicit, it would take a while. This is good enough for explaining what's going on here. Let me write this. If in the trivial case you have a real value 2 form, then there's no bundle curvature there, and then this is the Bachner formula for harmonic 2 forms on a 4 manifold. Okay, so back to the bundle setting, what's going on here is you have this term involving the bundle curvature. Now, when I was mentioning these gap results of Minnow and Parker, I said there's a certain positivity condition. So basically, they want to assume some condition between the self-dual part of the biotensor and the scalar curvature. What they want to basically do is throw out the second line here. Okay, so that really it's just this term and this term on the right-hand side. That's the basic idea. And then for the Born-Lawson, for the sphere, this term's gone. You just plug in the scalar curvature of the sphere, and it's just a competition between these 2 terms. That's where that's coming from. Okay, so we want to use this, but we want to use it. We want to first of all estimate these terms in as sharp a manner as possible. And then there's one sort of, well, at first it seems kind of remarkable, but then you realize it sort of has to be there. But let me explain. So claim, it's a series of claims, just basically estimating these terms. So first of all, what order should I do? I want to do it order over here. So if you look at the bracket term. So in absolute value, well, let me write it this way. So it appears the minus sign. I claim that's greater than equal to minus this constant gamma 1. In fact, you can take this as your definition of gamma 1. So it's just some algebraic constant. All right, depends upon the bundle. And then if you go through the linear algebra, you can see exactly what I wrote before, that it has universal bounds upon this. Okay, so again, just a linear algebra exercise, so this is nothing big. And then there's the Weil term. So it turns out that this really boils down to, when you take apart the action on these bundle value 2 forms, it really just sort of boils down to the estimate in the real value case. And the estimate you get is the same estimate you get in the real value case. So it's 2 root 6. Oh, wait, hold on, I have to divide that by something. Sorry. It's root 6 over 3, excuse me. The norm of the self-dual part of the biotensor times the norm squared of F plus, and this inequality is sharp. So this is 2. And then the other part, yes, so this is more involved. And again, this is something that is known in the real value case. It's actually due to Walter Seaman. But it holds in the bundle value case. If you have the Engel's connection, it says that the norm squared of the covariant derivative of the self-dual part is greater than or equal to 3/2 the gradient of the norm of F squared. And this 3/2 is sharp, and it's absolutely crucial for the argument. If it were worse than that, none of this would work. Well, at least our approach won't work. But it sort of has to be because of conformal invariance, it turns out. Okay, so if you put it all together, so 1, 2, 3, plug it into the Bachner formula, what you get. So you get the following. Well, actually, let me, all right, so I don't want to skip steps. Let me Yeah, I'll skip steps. So I estimate each one of these terms using the formulas about the inequalities above. I can't do anything with this term. It's as simple as you're going to get it. But here's the deal. When I estimate this to be the Kato inequality, I still have a term over here that involves the derivative of the norm. So what I want to do is basically get rid of that positive term so I can absorb it and it can help me. Is I look at power, it turns out to be precisely 1/2. Okay. So that makes that term go away. And then you have an inequality. So you can think of the following as holding away from the zero locus of f plus, or in a sense of distributions, however you like. And then when you get over here, and this is sort of the magic, with this choice of power that's driven by the sharp constant in the Kato inequality, combined with the fact that you have a 1/3 here, it's all interplaying together, and you get a 1/6. And that's going to be crucial. So, and I'll just collect all the terms under this 1/6. So it's r minus 2 root 6 norm w plus minus 3 gamma 1 norm of f plus times that power of f plus. So it's exactly this 1/6 coefficient that shows up in the formula for the conformal Laplacian and also the modified version. So you recall this. So we take phi to be, so my modified scalar curvature I want to study for this problem is, so I did general statement over there. Instead of looking at the Weyl curvature and the curvature of the Yang-Mills connection, I was looking at the self-dual parts. And I'll take my first constant to be 2 root 6, and I'll take my second constant just to be 3 gamma 1. So this is my modification of the scalar curvature, so I just collectively call this phi. And then what's the conformal transformation law of that? That was that operator script L. So in 4 dimensions, that's minus 6 Laplacian plus phi. So this was the operator whose first eigenvalue, such that the sign of the first eigenvalue is a conformal invariant. That's exactly the operator you're looking at here. So in fact, I can rewrite this big long inequality here very compactly as 0 is greater than or equal to L applied to f to the 1/2 power. So this immediately says that the first eigenvalue of this operator is less than or equal to 0. Okay, so what I want to do now is apply the lemma. Okay, so I apply the lemma. I get a conformal metric so that the corresponding curvature quantity, this one here, has a fixed sign. It's either identically 0, or this is less than or equal to 0. So it's either identically 0 or it's strictly negative. Okay? All right, so I think I'm done with this. So the lemma over on the other board implies that there exists a conformal metric such that this modified, okay, so let me write it this way. So this modified scalar curvature is less than or equal to 0. So I write that out, and that's this. But let me put the other terms on the other side. Plus 3 gamma 1. I get this. All right, then you're done. You just integrate both sides. So if I integrate both sides with respect to the volume, so this is bigger than or equal to the Amabi invariant times the power of the volume, namely the square root of the volume. Right? Use Cauchy-Schwarz. In each case, I get a factor of the square root of the volume, which I just cancel out. So on the left-hand side, you end up with the Amabi invariant of your manifold. Over here, I get 2 root 6 L2 norm of Weyl, and then 3 gamma 1 L2 norm of L plus. So that proves theorem A. All right, so now the proof of theorem. Yeah, okay. Right, so it depends upon the bundle. So if you ask about sharp, I mean, okay, so the way to say it is, by definition, it's you take omega, any 2 form, bundle value 2 form, and you look at the inner product of omega with omega bracketed with itself, and you divide by omega cubed. So gamma 1, by definition, is the sup over all omega. So that's just the definition. Yeah, sorry. Yeah, that's just the definition. So then using some algebra, you can see that there's this universal upper bound. But you might have bundles for which this is small. You can write down bundles for which it's smaller. Yeah. Okay, so now on to what I do is the index estimate. Okay, so here the story. Yeah, I can do it here. Here the story kind of changes. Now we have to a little more background on this idea from spectral theory. Okay, so what we're doing is we're taking this Jacobi operator that comes from a second variation. We're viewing it as a kind of Schrodinger operator, of course, acting on sections of a bundle. Well, and we're trying to estimate the number of negative eigenvalues. Well, this is a very classic. If you replace the bundle setting with, say, domains in Euclidean spaces, is a very classical kind of question that comes up in mathematical physics. So, in fact, this is, I'll refer to this as the CLR estimate for inequality. So, who are CL and R? So, do you know how to pronounce? Swickle, thank you. So, I guess this is the dates. If I get this correct, it's back to 77, and then Rosenblum, I guess like 76. So these are independent, and very different proofs, in fact. So it's a case of 2 of them working, I guess, in the West at the same time with independent proofs, and then someone working in the East. So here's the statement. It's a really beautiful result. So it says the following, that to consider a Schrodinger operator of the form minus Laplacian plus V, and let omega be a domain in Euclidean space, at least dimension 3. Found it. So we're going to look at the Dirichlet eigenvalues of this operator. I'm going to look at the counting function that counts the number of non-positive eigenvalues. So n0s is the number of eigenvalues of s that are less than or equal to 0. And the CLR result is that this can be estimated by some constant, dimensional constant, times the Ln over 2 norm of the negative part. So I'll write this one, the negative part of the potential V. Okay, so as I said, these proofs are quite different, and as we spent a fair amount of time trying to see if there was any way to try to adapt them to our setting, we had this this operator on this bundle, on this particular bundle, and we couldn't see how to do it, which is still a very interesting question. But in any case, it turns out there was another proof of this result, appeared a few years later, and that was much more adaptable. So this was due to Li and Yao in 1983, and they gave an explicit constant of the following form. I just well, it doesn't really matter if I can write it down, but it won't really figure so much. It'll partly explain where our constants come from. So this was their constant. So in fact, the E and R constant really comes from this E and the Li-Yao, and again, it basically boils down to a trace of some heat kernel. So, and it turns out that the great thing about Li-Yao's estimate is that it immediately adapts to manifolds, where, their argument quickly adapts to manifolds that you're looking at, say, a closed manifold, and you drop the boundary condition. Right? So, in that case, if you apply the compact manifold, then if you trace through, you see that they're constant in their inequality now. It depends, of course, on the dimension, but how does it depend upon the metric? And it concretely depends upon the Sobolev inequality. So basically, if you have Sobolev constant control, then their argument runs. Okay, so I won't have time to take you through the proof of Li now, although actually it's fairly straightforward, but it's a little bit long. Each step is very natural and nice. So let me just tell you how we apply it. So we take their proof, but we also need an additional estimate, and we're able to put it into a vector bundle setting. And so our general results, so I'm going to state this in 4 dimensions. You can do something more generally, but it's not quite as nice. Let me just state it in 4 dimensions. And so novel is a connection. So this is a metric compatible connection. We're out of the Yang-Mills setting. I just want to be able to define a rough Laplacian so I can define the Schrodinger operator. That's all that's going on here. And so by the connection, I can define a Schrodinger operator. So, but I want to look at a very special kind of Schrodinger operator. I want one that looks like to leading terms. This is acting on sections of the bundle, but I want the leading term to basically look like the conformal Laplacian, same coefficient here, and then V minus potential. So it's acting on sections of your vector bundle, and I assume that V is non-negative. All right, then it's just a matter of running through. So we use the Li-Yao proof, but there's a key point where, so their proof is for Laplacian acting on functions. We need it for operators acting on sections of vector bundle. And there comes a point where you have to say that there's some comparison between traces of heat kernels of rough Laplacians on sections of the bundle versus the Laplacian acting on functions. Right? So for that inequality, so there's actually a number of results in that line, but we use an argument of Li and Donnelly, or Donnelly and Li. In any case, putting it all together, what you get is the following estimate, that if the Amabian variant of your base is positive, then you can estimate the number of negative eigenvalues of your Schrodinger type operator here by 36e squared divided by the square of the Amabian variance, that's where that comes from, and then times the rank of the bundle, and then times the L2 norm of V. I guess it's L2 norm squared, sorry. Okay, so even knowing that, actually, it's not a plug-and-play kind of result. Operators in second variation of the Yang-Mills function, I'll plug it into this and get any kind of estimate, get an estimate that even resembles what we did. So I need to spend a few minutes to explain how you get from that to our conformally variant estimate. Keep that up there. All right. Oh, and I should also say, if I have time, what I'd like to do is, so now what I do is I want to take this estimate, I do want to apply it to the Jacobi operator for the Yang-Mills function, but after we do a conformal change of metric that's in the same spirit as we talked about for the proof of theorem A, and then show how eventually this index estimate of ours pops out. But I also want to show that this can be applied to prove other kinds of index estimates. So at the end, if I have time, I'll try to quickly show how this can be used to estimate the index of Einstein metrics, which is a different kind of problem, but it turns out the Jacobi operator has some similar structures. Okay, so now what I want to do is a sketch, a proof, theorem B. Right. So how does it go? All right, so step 1, we're going to, again, do a conformal change of metric, and it's very similar to what we did before. So now I want to kind of tweak the curvature a little bit. So remember the operator we looked at was some modification of the scalar curvature, and I had 2 root 6 W plus here, and then 3 gamma 1, more of the curvature there. So I want to drop the pluses, because it turns out that the Jacobi operator, you can't detect the self-dual part and the anti-self-dual part. So let me drop those. Right? And then I want to put a parameter t here.